Welcome to Wednesday's Algebra 2 class. I want to say, first of all, I'm very impressed that I saw that a lot of you did go on and view this lesson from yesterday, so that's fantastic. I also received quite a few of you already submitting the homework through the Google Docs, and that's great. You'll notice that it is on your instructions to do that today if you haven't already done so for yesterday's homework. And I did get a few of you asking some questions, and a little bit later I'm going to be producing the homework helps video to go along with assignment number 74, so be on the lookout for that. I will put a link on the web page for that. But here we are at the beginning. I'm going to say, Jesus, please help everybody to understand when we go over things today, and help everybody with all their needs. In your name, amen. And so off we go on chapter 6, section 2, about multiplying and dividing radical expressions. Remember, a radical is this symbol right here, and n is our index, and these numbers in here would be our radicands. And what we're going to do is take a look at some of the rules and how to put things together involving these radical expressions. It acts an awful lot like an exponent because it really is a hidden exponent. We're not getting to that so much today, but if the rules seem similar to the exponent rules, it's because they really are very much similar. So as long as your index is the same number, it's okay to take your radical and combine the things that are under two different ones and put them together. Now, there are a couple of exceptions to that we will kind of get to as we go through other sections, but for right now, the quick rule is as long as the index is the same, you can bring it all under the same radical and then simplify. That is especially true when you have odd indices. The odd indices, believe it or not, are easier to deal with than the even indices. Okay, so in this, let's take a look at these two examples and how you would actually put these things together. Notice that these both have a radical or an index of 3. So these can get put together, and when we actually begin to simplify this, this becomes the cube root of -8, because the -4 and the 2 can get put under the same. And then when we're looking for the cube root of -8, remember what you're doing is you're saying what number times itself, where there are 3 of them, will give you -8. And of course our answer is -2, because -2 times -2 is 4, times -2 is -8. So the answer being -2. These two, however, notice that this has an index of 3, this one has a hidden index of 2. So we can't combine them. These have to stay separate. They're two different radicals, two different indices, and so for now we can't combine them. For those that maybe had an upper level math course that are checking in on the YouTube channel, we have tricks once we get to discussing the fractional exponents, but for now, when you have two different indices, there's no way that we're going to be able to combine them, and I want you to just hold on to that idea. And as we move along, if we're looking for a cube root and we're trying to figure out how those work, I think I skipped a few. Wait a minute. Let's go back here. Yeah, I did skip quite a few. Something happened. Okay, here we go. This is where we belong. So what we want to do is we do want to be able to reduce to simplest form. We had talked about square roots before, where you can reduce those to simplest form. Cube roots have a similar process. Fourth roots have a similar process, but instead of looking for groups of 2 like you do in a square root, you're going to be looking for groups of 3 in a cube root. I'm going to open up an extra tab here. Okay. And we want to prime factor our 24 so you can get the pieces of it. Just like when we did square roots, we have 8 and 3, we have 2 and 4, and we have 2 and 2. So if you remember from square roots, what we would be doing is we'd be looking for pairs. So if we have a pair of 2's, you'd be able to bring 1, 2 outside of the radical, and the 2 and the 3 that are left over would have to be inside the radical. So your simplified form of this expression will be 2 times the square root of 6. 1, 2. You're looking for pairs because it's an index of 2. This part is really a 4. Remember, square root of 4 is 2. That's why that can come out. This part, there's no partners, so it can't. When you have a different index, though, you can do the same beginning steps where you're taking 2 times 2 times 2 times 3. But instead of looking for groupings of 2, you're looking for groupings of 3. So here we have 3 2's, which would make an 8. And the cube root of 8 would give me 2, so one of the 2's can pop out. And we have a 3 left over that doesn't have anything else for the group. So that's in essence what you're looking for in these particular types of problems. Here's what this looks like. There's our simplified form for the square root of 24. And here's our simplified form for the cube root of 24. The index, once again, tells you how many you need to bring 1 out of in order to simplify. Looking for groups of 2 here, groups of 3 here. It's all found in the index. Now, it's always a good idea as you're going through these videos to pause, and if you're like, wait, I think I can do this, go ahead and do it, and then just kind of look to see if you got the right answer. The more you can think through things on your own, the better off you will be. So cube root of 54, if you prime factor it, you're going to get 2 times 3 times 3 times 3 x to the 5th, just for the number part. So the number part of our radicand, you've got 3 3's. So 1 3 can pop out. So that's our first part. 1 3 pops out, and you're left with a 2 that's going to stay underneath of the radicand, the radical, sorry. And x to the 5th is still there. But we need to deal with this x to the 5th. We will be looking for groups of 3 x's. So if you recall, our way of handling that would be divide the exponent by the index. So taking our exponent and dividing it by the index, 3 goes into 5 one time, and when you subtract here, you have a remainder of 2. Both of these things are going to be important. The whole number of times that your index goes into your exponent tells you how many of that particular element will come out of the radical. So 1x can come out, and imagine the 5x's all lined up. You'd have a group of 3, so 1 comes out, and then the remainder tells you how many remain under the radical. The only thing that's different than what we were really doing before with the square roots is that we now just have a different index. So you're dividing by a different number. You're looking for groupings of a different number of elements that are underneath. Let's look at another one. Cube root of 128x to the 7th. What I would suggest that you do before I show the next slide is pause and just work this out and see if you can fast forward a little bit. Here we have 128. When you factor it, we get a whole bunch of 2's. 1, 2, 3, 4, 5, 6 of them. 7 of them, sorry. Do we have 6? 1, 2, 3, 4, 5, 6, 7. There we go. Here's our 7th. 1, 2, 3, 4, 5, 6, 7. So we have 7 of them. Here's 3 2's here, 3 2's here. One more 2. And then x to the 7th. So 1, 2 2's come out. And we still have our x to the 7th to deal with. As you get better at these, you're going to be able to do this all in one step. Or you might even notice that it's 2 to the 7th. You can use the whole exponent dividing thing with these two, although once you've prime factored it, it's just as easy to do group of 3 2's, group of 3 2's. 2 2's come out, 1 2 left over. Divide 7 by 3, and we get 2 with a remainder of 1. So 2 x's are going to come out, and 1 will remain under the radical. Also, the 2 times 2 gets simplified, so in our most simplified form, we have 4x squared times the cube root of 2x. Hopefully you're not finding this too difficult, it's just new. Each math concept, remember, builds on some other things that you know, and you can do this. Now we're going to combine what I talked about earlier. We have square root here, we have square root here, so you can, before you simplify, you could simplify these things individually and then put some things together, or you can just bring them all under one radical and simplify all at once. And that's the method I'm going to show you right now. So since I have both of them being square roots, I can just make this into 720, x to the 4th, y to the 5th. Because you can keep the same radical, it's got the same index, you can put them together. I want to factor the 720. Now, the 720 we already know came from 72 and 10. We may as well start there. Then 2 and 36, 2 and 5. Remember, when you're prime factoring, you can, if you saw different factors first, you could do that. You're still going to end up with all of the same factors when you go through and you find all of the numbers that go into 720. We have 1, 2, 3, 4 2's, 2 3's, and a 5. So you're looking for pairs once again, a pair of 2's, a pair of 2's, a pair of 3's. And so 2 times 2 is 4, times 3 is 12. Each one of them came out. I did take the liberty of simplifying as they were brought out this time. We can understand that 4 divided by 2 gives you 2 x's that come out. 5 divided by 2 gives you 2 with a remainder of 1, so 2 y's come out. We have a square root and 1 leftover 5 in there and 1 leftover y in there. So this would be our simplified form of that. All right, then we come to fractions with the same index. So I've got an index of n here, an index of n here, and you can combine them just like you can with multiplying into one overreaching radical. And when we begin to work on problems, a lot of times the easiest thing to do is make them into one big fraction first before you start doing these things, before you start simplifying. So we're going to take a look at it doing it in that way. So I'll make one big square root here, 18x to the 5th over 2x to the 3rd. And then you can simplify this by dividing, so you've got a 9. And then don't forget, we've got 5 x's up here, 3 x's down here. You can cancel out, so you end up with 9x squared. Then when you take the square root of 9 is 3, and the square root of x squared is x, and we end up with a 3x there. Now, when we do the cube root, when we do the index of 3, once again, it's the same process, but you've got an index of 3. So we'll bring over our 162. 162 is divisible by 3. When you divide that out, you get 54. And the y to the 5th over y squared. Remember, like bases, subtract exponents for dividing, and we end up with y cubed. So then we go to our prime factoring of 54, which when you did that, you would get 2 times 3 times 3 times 3, and a y to the y third. One group of 3 3's, so that can come out. A 2 left over, and a y also can come out because there's a group of 3 y's. And so using these ideas of putting together actually makes it very, very simple to simplify these things. Now, another thing that happens when we simplify and we're dealing with radicals is that in math, we don't like to have a radical in our final answer in the denominator of a fraction. It's just a standard way that these are written. So what we need to do is we need to find ways to make it so we have a whole number or an integer in the denominator. And we can do that by thinking about how much we need to make the amount of 2's under the radical in the denominator in order to get rid of that radical. And the way we think about that is that in order to bring out 2's, I would need a pair of 2's. So I need another one down here. Now, if I just multiply a denominator by square root of 2, you can't do that and keep the same value, but you can always multiply something by 1 to keep the same value. So this right here is just a very strange looking 1. Anything over itself gives you 1. So when I multiply by square root of 2 over square root of 2, the result is going to be, and I know we're used to canceling out, but in this case we're not. We're just going to multiply the numerator and get square root of 2. And in the denominator, we have the square root of 4 because you can put these together because they're the same type of a radical. And the square root of 4 turns into a 2. And all of a sudden, this answer has been simplified. Now, your minds, because you're not probably used to seeing this yet, you might think, wait, I thought the original thing looked way more simple. But in math, there are some standards as far as simplifying. And when you simplify these, you can't have a radical in the denominator for your final answer. So that's just a little something that you need to just any math course you take, you're always going to be simplifying so you don't have a radical in your denominator. Same thing works for the cube roots. We're going to rationalize the denominator. That's the word in math that we use to mean so that you don't have any radicals in the denominator. So you're looking for what else we need in order to complete groups of 3 in here. So we have 1 5. That means we need 2 more 5s to make a group of 3. We have 2 y's. That means we need 1 more y in order to make a group of 3. So in order to solve this one, in order to simplify this one, we need to get a cube root of 5 times 5 times y to put with this in order to bring things out of the denominator. So remember, anything over itself is 1. So the way that you figure out what goes in here is by what more do I need to make groups of 3? Because here, what we have is we have 7, 5, and 5, and x and y in the numerator. We put it all together. And here in the denominator, we have your 3 5s, and we have your y to the third. And when we simplify this, the numerator, all you're doing is making it look nicer by doing 7 times 5, 35 times 5. And then in the denominator, you've got a group of 3 5s, and you've got a group of 3 y's. So it just turns into a 5y. So once again, to fully simplify, you need to make sure there's no radicals in the denominator. In other words, we rationalize them. We make them into rational numbers. And one more. What would be the best thing right now would be for you to pause this and try to wrestle through this on your own, and when you're done, unpause, and then you can hear what I have to say on it. All right, so we're looking for, after you prime factor the 12, 2 times 2 times 3, you need to figure out how many more I need to make a group of 3, which would be 1, 2, and 2 3s. We need another y, and we need 2 z's. Because this will give me 1, 2, 3 2s, 1, 2, 3 3s, 1, 2, 3 y's, 1, 2, 3 z's. And remember, you're always multiplying the numerator and denominator by the same thing. Then you scoop them all under the same denominator, or same radical. And in the denominator, you bring all those things you just put in. So what we have is we have a group of 2's to come out. We have a group of 3's to come out. We have a y to come out and a z to come out in your denominator. 2 times 3 times y times z. Here, all you're doing is simplifying. 5 times 2 is 10, times 3 is 30, times 3 is 90. So we have a cube root of 90 there. Nothing can come out because there's no groups of 3's there. And an x squared and a y and a z squared. And that's it. I do need all of my students who are in my class to go ahead and fill out that exit form that I've got on your page, and let me know if there's anything that you need help with. You're also making sure to turn in your homework assignment using the form link that is also on the page. And that's about it for today. I hope you all have a fantastic conclusion to your day.